Hi friends, welcome to your lesson on auditory processing and sensation. We're going to start this lesson with audition, but before I do, I'm going to just go ahead and say this is a much shorter lesson than visual because we don't have all of the stuff that we had on perception like we did in visual. All of that stuff is really awesome. It was just a little bit longer of a lesson. So, starting with audition. Audition is the sense or act of hearing. And this diagram you're going to see several times throughout the lesson. So don't feel like you need to jot it down right now or anything. Okay. And it's also in your notes, and so you don't have to jot it, but it's also going to be part of your shelf work for your explore work. So how do air pressure waves become sound? If you draw a bow across a violin, you will unleash the energy of sound waves. And what happens is air molecules bump up to each other. And that creates waves of compressed and expanded air, like the ripples on a pond whenever you toss a stone into it. And as we swim in our ocean of moving air molecules, our ears detect these brief pressure changes. So the waves, compressed meaning close together or expanded meaning not close together, determine what we hear. So characteristics of sound waves. So we're going to review this like we just reviewed. Sorry, that was a walkie. I'm at school. Like we just reviewed for vision and the electromagnetic spectrum, and the part of the electromagnetic spectrum that we see, we talked about wavelengths and amplitude. So again, this is the same slide as you had in that last lesson. The shorter wavelength means you have a shorter distance from crest to crest, and a longer wavelength means you have a longer distance from crest to crest, and a longer wavelength is associated with low-pitched sounds, and a shorter wavelength is associated with higher pitched sounds. Amplitude, on the other hand, is how tall the wave is. And so a tall wave, great amplitude, means loud sounds, whereas a small amplitude wave would have softer sounds. So what information do sound waves give us? Well, what pitch am I hearing? So pitch, again, short wavelength, is going to be a higher pitched sound, and a long wavelength is a lower pitched sound. And long, low, both start with an L. That's a good way to remember it. Short has an H in it. High pitched starts with an H. So how loud is the sound I'm hearing? The bigger amplitude, louder sounds. Smaller amplitude, softer sounds. So exam tip number 1, note that both light and sound travel in waves. In each case, the amplitude and length of the waves are important to learn for AP exam. So you saw that slide in the last lesson on vision. So go back and look to it and now compare it to what you know about wavelength with hearing. Okay, so getting into the divisions of the ear. There are 3 divisions of the ear. They're divided into outer, middle, and inner sections. How does the ear transform sound into neural messages? So, passing through accessory structures to sense receptors, vibrating air triggers nerve impulses that the brain decodes as sound. Pretty cool. So going through these parts, what's the auditory channel? So if you look towards the outer ear, starting on the left-hand side where you see the sound wave coming in, the not auditory channel, it's auditory canal, which is the channel located in the outer ear that funnels sound waves from the pinna to the tympanic membrane. That's a fancy word for eardrum. So it's really from the outside of your ear into the inside, into your eardrum. What is the eardrum? What is the tympanic membrane? The eardrum is a thin layer of tissue that vibrates in response to sound waves. Pretty cool. So the sound waves enter your ear. The tympanic membrane, that tissue, starts to vibrate in response to the sound wave that you're hearing. Ossicles are made up of the 3 smallest bones in the human body, the incus, the malleus, and the stapes. They transfer the sound wave vibrations from the tympanic membrane to the oval window of the cochlea. And so if you look, again, starting on the outside, going into the eardrum, you see those bones of the middle ear, the 3 bones of the middle ear, into the, they transfer that into the oval window of the cochlea. That's where the stirrup attaches. So the oval window is that blue piece, the blue piece in the diagram towards the right-hand side. The oval window, that blue piece, is the membrane-covered opening of the cochlea. It vibrates when it receives sound waves and causes the fluid inside the cochlea to move. And we're getting to the cochlea, so hang tight. The cochlea is a coiled, bony, fluid-filled tube in the inner ear. That's that coily. You can see cochlea on the right-hand side, the blue coiled part. Sound waves travel through the cochlear fluid, and as they do so, they trigger nerve impulses. So AP exam tip number 2, you might notice that some sensory structures are referred to in more than one way, such as the tympanic membrane, that's also known as the eardrum. The Latin designation is important to know. So don't just know eardrum and throw away tympanic membrane. Please do remember tympanic membrane is a synonym for eardrum. And the textbook has simplified the terms and uses eardrum, but learn both names and understand that they refer to the same structure. So if you see it on the AP exam, you won't be confused. How does the sound wave move through the inner ear? So we've just moved through the cochlea. So now we're into the inner ear. Accessory structures move the sound wave to the sense receptors, which are stereocilia, in the inner ear, where the wave energy undergoes transduction to neural energy that the brain can interpret. And I'm going to break that down for you in just a minute. So look at the diagram, and you see on the left-hand side, this is now zoomed in from what compared to what we were looking at, and we are at the oval window and the cochlea. The partially uncoiled cochlea is the blue and the red part on the right-hand side. So how does transduction occur in the inner ear? The motion of the sound vibration against the oval window, which is that section that you see, it's the stirrup, the eardrum, the stirrup, and then the oval window. It's the very left side of the cochlea. When the sound vibration hits the oval window, the cochlea causes ripples and the basilar membrane, bending the hair cells lining its surface. So there's hairs all along that protruding. You see the basilar membrane, and then the protruding hair cells. When it comes through, those hair cells start to move. Although basilar membrane is not considered a key term, it's considered a key term on the AP exam. Free response questions and multiple choice questions frequently ask about the basilar membrane, so make sure to learn about the way sound waves are transduced into neural impulses via the cilia on the basilar membrane. And cilia, you might remember, is a term from biology if you've had biology. If you haven't had biology, you will have it. And you also all had it in middle school when you learned about cells. Cilia, cells and prokaryotes and eukaryotes. Cilia, remember, are what help them move and often protect from things. Okay, so moving on, how does the nerve impulse move out of the ear then? So the hair cell, the cilia, movements, they in turn trigger impulses in adjacent nerve cells. So the little tiny hairs moving around, and that triggers an impulse in nearby nerve cells. And those axons in those nearby nerve cells converge, so they come together to form an auditory nerve, which is so cool. Now, how does the message carry to the brain? So that auditory nerve then carries the neural messages to your thalamus and then onto the auditory cortex in your brain's temporal lobes. Super awesome. We're bringing it all back to the parts of the brain that we just spent so long studying and tying in neurons and the parts of the neurons with the axon. Okay, so exam tip 4 for this lesson. Pay attention to how many pages are devoted to each of the senses. Not only does this represent the complexity of the sensory system, it also represents how likely you are to find questions about that system on the AP exam. Given that more pages are devoted to vision than hearing, there are likely to be more exam questions on vision. And this is referring to your textbook. And so I know in your notes, not your notes, on your checklist, I put page numbers. Just check that out and flip through it and look at some of the diagrams and look at some of the real world examples so that you have just more practice with it, as well as you know that this lesson is much, much shorter than the vision lesson. The vision lesson was a honkin' 30-minute lesson. This one is definitely not. Okay, so 2 types of hearing loss: sensorineural and conduction. Sensorineural hearing loss is when there's damage to the cochlea's hair cell receptors or the auditory nerve, and that can cause sensorineural hearing loss. When with auditory nerve damage, people may hear sound but have trouble discerning what someone is saying. Now, conduction is damage to the mechanical system, the eardrum and the middle ear bones that conduct sound waves to the cochlea. Can actually cause conduction hearing loss. This kind is less common than sensorineural hearing loss. So how much sound is too much sound? As a general rule, any noise we cannot talk over, loud machinery, fans screaming at a sports event, music blasting at maximum volume, may be harmful, especially if prolonged and repeated. That is probably why I speak so loudly, because I listened to loud music a lot when I was younger and still kind of do on the way to work. I love my music, singing in the car, and prolonged exposure above 85 decibels actually produces hearing loss. So it is not something to mess with. What's the problem with headphones? Headphones direct all the sound waves into the auditory canal and bombard the basilar membrane. In the open air, however, when you don't have headphones on, sound waves disperse and are not at all directed to one location. So it's especially important to be really careful when you're wearing headphones, not to overdo your volume. How can headphones actually help? Well, when Super Bowl winning quarterback Drew Brees celebrated New Orleans' 2010 victory amid pandemonium, he used earmuffs to protect the vulnerable hair cells of his sweet son Balin. So that can actually, earphones or headphones can actually help with that. Miss Megan, her sweet baby Miles, he goes to Panthers games and they have earphones for him so that his little ears are protected. Okay, so research on hearing loss. Since the early 90s, teen hearing loss has risen by 1/3 and now affects 1 in 5 teens. Well, why do you think that is? Well, headphones, cell phones, headphones, earbuds, all that. After 3 hours of a rock concert averaging 99 decibels, 54% of teens reported not hearing as well, and 1 in 4 actually had ringing in their ears. Teen boys more than teen girls or adults blast themselves with loud volumes for long periods. I don't know if I agree with that completely, because I do, but I think in general, overall, those are the statistics. So a cochlear implant is a device for converting sounds into electrical signals and stimulating the auditory nerve through electrodes threaded into the cochlea, which assists with hearing. It works by transplanting sounds into electrical signals that are then transmitted to the cochlea and via the auditory nerve relayed to the brain. And so this is what you're seeing when you see someone who actually has a cochlear implant. There is a transmitter on their head that's connected to the speech processor underneath their ear, and then it comes into their ear and connects. There's an electrode that connects to the cochlea, which that is that purple blue piece in the diagram. How does the brain detect loudness? So a soft tone activates only the few hair cells attuned to its frequency. Given louder sounds, however, neighboring hair cells also respond. So the brain interprets loudness from the number of activated hair cells. If you have like a head of hair moving around, not literally a head of hair, but a lot of nerve hair cells moving, That means it's a loud sound. What is one theory of how the brain detects pitch? So place theory presumes that we hear different pitches because different sound waves trigger activity at different spots along the cochlea's basilar membrane. Thus, the brain determines a sound's pitch by recognizing the specific area on the membrane that's generating the neural signal. Frequency theory is also called the temporal theory, and it suggests an alternative, that the brain reads pitch by monitoring the frequency of neural impulses traveling up the auditory nerve. The whole basilar membrane vibrates with the incoming sound wave, triggering neural impulses to the brain at the same rate as the sound wave. If the sound wave has a frequency of 100 waves per second, then 100 pulses per second travel up the auditory nerve. How does the volley principle explain hearing higher frequency sounds? Well, by firing in rapid succession, neurons can achieve a combined frequency above 1,000 waves per second. So like soldiers who alternate firing so that some can shoot while others reload, achieving greater combined firepower, neural cells can alternate firing to do the same thing. So the two theories work together to explain how we hear pitch. Place theory best explains how we sense high pitches, and frequency theory, extended by the volley principle, also explains how we sense low pitches. Finally, combination of place and frequency theories explain how we sense pitches in the intermediate range. And last, how do we locate sounds? Sound waves strike one ear sooner and more intensely than the other. From this information, our brain can compute the sound's location, which is so cool. So if you hear it, if this picture, for example, in the diagram, you can see on the left-hand side, there's a sound shadow. So that bell, when it's rung, because it's on that person's right-hand side, is going to travel through the air, those sound waves travel, and it's going to hit the right ear first, which is going to tell you that that sound is coming from the right-hand side of you. Cool stuff. All right, guys, I kept it to 17 minutes. I hope you have a great day or night or whatever it is you're reading this and watching this, and I'll see you in class. Ciao.